Hello everyone. Today we'll be discussing about integration by substitution. Algebraic substitution. Algebraic substitution is the first of the many substitutions that we can apply in order to integrate an integrand. The method of algebraic substitution deals with the integrals of irrational functions or with irrational integrand. The irrational integrand is transformed to one that is rational by substitution of a new variable. The algebraic substitution depends on the irrational integrand under consideration, and no general rule is given. There is, however, one cruel rule of thumb which succeeds often enough to make it worth consideration. Determine what quantity seems to be causing difficulty or trouble from performing basic integration. Then introduce a new variable for that quantity. Let us consider integrating sine square root of x dx. If we will be integrating sine square root of x dx, let us first observe that there is this term square root of x that makes the expression a little bit complicated. So, we let z be equal to square root of x. We're going to solve for x from this expression, so that would be x equal to z squared. And after which, we solve for the differential dx. So dx would be 2z dz. We are going to plug in now square root of x is equal to z and dx equal to 2z dz. So from the original integral, we have sine square root of x. So sine z and your dx is 2z dz. So we have 2 and then z sine z dz. This is an indicated product of two expressions z and sine z. So if there is an indicated product of two expressions, we can use integration by parts. So in Liate, L-I-A-T-E, so we prioritize logarithmic, followed by inverse, and then algebraic. So the algebraic term z would be your u, and the remaining terms sine z dz would be your dv. So your u dv is z sine z dz. And with that, we take the differential of u, which is dz, and we take the integral of dv, which is negative cosine z dz. We plug it into the formula uv minus integral of v du. That is the integral of u dv. So u z times v negative cosine z minus the integral of v, which is negative cosine z dz. So with this, we have negative 2z cosine z, and then we distribute 2 to the other term. So we have 2, and then negative of negative would be positive cosine z dz. We can now integrate cosine z dz, and that would be positive sine z. And thus, we have negative 2z cosine z plus 2 sine z plus c. Take note that z is the square root of x. So we plug in z is equal to square root of x. So we have negative 2 square root of x cosine of square root of x plus 2 sine square root of x plus c. For our second example, we have dx over 1 plus square root of x. For this, we're going to do the same substitution. Z is equal to square root of x. Z squared is positive x. And its differential dx is equal to 2z dz. We're going to plug that in to the equation or to the function, the integral dx over 1 plus square root of x. So dx is 2z dz, and 1 plus square root of x is equal to 1 plus z. So we have 2 integral of z dz over z plus 1. We're going to apply division to this one, so we can have z over z plus 1. We can add and subtract suitable term. We add 1 and subtract 1. So we have z plus 1 over z plus 1 minus 1 over z plus 1. So thus, we have 1 minus 1 over z plus 1 dz. So, applying linearity property, so we have the integral of 1 dz or integral of dz minus the integral of dz over z plus 1. These two terms are integrable. So 2 times the integral of dz is 2z, and 2 times the integral of dz over z plus 1 is ln of z plus 1. And do not forget to return the original variable by letting z to be equal to square root of x. So we have 2 square root of x minus 2 ln of square root of x plus 1 plus c. Now, let us consider this problem. 5y plus 4 dy over the square root of 5y minus 1. So, the entire term in the denominator makes it a little bit complicated. So, if we can just set this to be your z, it might look simpler. So, we let the entire denominator square root of 5y minus 1 to be your z. And after that, we solve for y. So we square both sides of the equation. So we have z squared is equal to 5y minus 1. So z equal to square root of 5y minus 1. Squaring both sides, so we have z squared is equal to 5y minus 1. And then solving for y, so we have z squared plus 1 all over 5. We can now differentiate this. So we have dy is equal to 2z dz all over 5. We are now going to apply this substitution to our equation. So we have the integral of 5 times y. Y is z squared plus 1 over 5 plus 4 dy. So dy is z squared plus 1. Dy. Dy is 2z dz all over 5. While square root of 5y minus 1 is equal to z. So with this, we can factor out 2 over 5. So we have 2 over 5. And then 5 over 5 would cancel out. So we have z squared plus 1 plus 4 times z over z. So this z would cancel out to the denominator z. So we have z squared plus 5 dz. So, factoring out 2 over 5, and then we have integral of z squared dz. So, that would be z cubed over 3. And then we have 2 over 5 times 5, which is 2. So, the integral of dz would be z. So, we have now 2z plus c. So, 2 over 15. So, this is, we can simplify this as 2 over 15 z cubed plus 2z plus c. You can factor out z, and then we have 2 over 15 z squared plus 2 plus c. So we have z, the LCD is 15. So we have 2z squared plus this is, I think, 30 plus c. So we have z times 2. Z squared is 5y minus 1 plus 30 all over 15 plus c. So we have z is square root of 5y minus 1 times 2 times 5y. So that is 10y minus 2 plus 30 all over 15 plus c. So that would be 10y plus 28 over 15 times square root of 5y minus 1 plus c. We can factor out 2. So we have 2 over 15 times 5y plus 14 square root of 5y minus 1 plus c. And this is your final answer. Now, for this next item, we have the integral of square root of e to the x minus 9. So, we let the entire radical to be your z, and we square that, so we have z squared is equal to e raised to x minus 9. And we differentiate this, so we have e to the x dx is equal to 2z dz. And with that, we have dx is equal to 2z dz over e raised to x. But your e raised to x is equal to z squared plus 9. So we have 2z dz over e to the x, which is z squared plus 9. So we have now the integral of the square root of e to the x minus 9 is equal to z. And then dx is 2z dz over z squared plus 9. So we now have 2 times z squared dz over z squared plus 9. So we can apply addition and subtraction of suitable terms. So we add 9 and subtract 9 such that if we divide it by z squared plus 9, we will be having 1 minus 9 over z squared plus 3 squared. So we have this one as the integral of dz, 1 dz. And then we have 9 times 2, 18 dz over z squared plus 3 squared. So 2 dz would have an integral 2z, and then factoring out 18, the integral of du over u squared plus a squared is equal to 1 over a arctangent of u over a plus c. For this problem, you have u is equal to z and your a is 3. So we have 1 over 3 arctangent of z over 3 plus c. And thus, we have 2. Z is equal to u. So z is equal to square root of e to the x minus 9 minus 18 over 3 is 6 arctangent of z over 3, with z being equal to square root of e raised to x minus 9 over 3. So do not forget the plus c in your integral. For our next item, we have integral of dx over x raised to 1/2 plus x raised to 1/3. So we have to let your z be equal to a certain term such that we would be removing the radical later. So what we do is to find the LCM of 2 and 3, and that is 6. So that would be the power of our substitution term. So x is z raised to 6, such that when we differentiate it, dx, we have 6z to the 5th dz. So we plug it in to our equation. So we have integral of dx. So that would be 6z to the 5th dz all over x raised to 1/2. Your x is z raised to 6 raised to 1/2 plus z raised to 6 raised to 1/3. So we have the integral of 6z to the 5th dz over z cubed plus z squared. So that would be this equivalent expression. We can divide both numerator and denominator by a certain power that would simplify the expression. In this case, we can divide both numerator and denominator by z squared. So we factored out 6 and we now have z cubed. And then for the denominator, we have z plus 1. So we have z cubed to be divided by z plus 1. So we have z cubed as z squared. So z squared times z is z cubed plus z squared. So we now have negative z squared. Negative z squared divided by z is negative z. So we have negative z squared minus z. We can cancel this and we have positive z. So plus 1. Z plus 1 is the product and the remainder is negative 1. So this is to be written as minus 1 over z plus 1. So we have z squared minus z plus 1 minus 1 over z plus 1 dz. So we can now integrate this, taking note that the factored out constant will not change the integral. No? So we can factor it out. So we have z cubed over 3, z squared over 2, z, and ln of z plus 1. And do not forget the constant of integration. So 6 over 3 is 2, z cubed. So take note, we have 2 z cubed minus 3 z squared plus 6z minus 6 ln of z plus 1 plus c. But take note that z is x raised to 1 over 6. So 2 x raised to 1 over 6 cubed minus 3 x raised to 1 over 6 squared plus 6 x raised to 1 over 6 minus 6 ln of x raised to 1 over 6 plus 1 plus c. So 2 x raised to 1 half minus 3 x raised to 2 over 6 plus 6x raised to 1 over 6 minus 6 ln of x raised to 1 over 6 plus 1 plus c. So we now have 2 square root of x minus 3 cube root of x plus 6 sixth root of x minus 6 ln of the sixth root of x plus 1 plus c. That's all for our example for algebraic substitution. We can now stop the video and watch the upcoming videos about algebraic substitution.